तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
So, we have now come to the end of this course. In this course, we have studied various aspects of digital integrated circuits, and mostly we have concentrated on the components, that is the effect of the different components on the performance of the circuit. In today's class, we shall take up another an aspect which we have not discussed so far, that is the effect of the interconnects. That is, if we have a digital circuit, say for example a NAND gate, which is driving another NAND gate, there is a line which carries the signal from the output of one gate to the other. So, this is an interconnect. Now, what is this effect of this interconnect? Now, we normally expect that the signal at the input of the next gate of the gate which is being driven is identical as the identical to the signal at the output of the driving gate. That is, that this is a short circuit and there is no difference between these two at the input of this gate and the output of the other gate. But it is not always true. The interconnects have a lot of effect on the performance of the digital circuits, especially in today's world, where with the shrinking of device dimensions, the gate delays are reducing, have reduced tremendously, while this effects of the interconnects have remained as before. So, in fact, the delays of modern day integrated circuits is controlled to a large extent by the effect of these interconnects. Okay, so in today's class, we shall take up the effect of the interconnects on the performance of the digital integrated circuits. Okay. Now, this digital integrated, these interconnects have a number of different effects. For example, it may cause a delay of the signal, that is, the signal which is going from the output of this gate to the input of the other may get delayed, and also that it may cause distortion. Okay, that is, the nature of the signal at the input of the driven gate may be different from the nature of the signal at the output of the driving gate. So, that may cause a lot of problems. So, we have to understand these effects and try to take remedial measures. So, in today's class, we shall see the different effects of the interconnects on the performance of the digital circuit. This interconnect line, which transmits a signal from one point to the other, is called a transmission line, can be modeled as consisting of an inductance, resistance, and capacitance, and a conductance. So, L, R, C, and G. Now, these components are distributed throughout the line. So, these are not lumped components, but these will be distributed throughout the interconnecting line. So, this usually for a unit length of the line, so this L will represent the inductance per unit length, R the resistance per unit length, C the capacitance per unit length, and G the conductance per unit length. Okay. Now, so this is the equivalent circuit of a transmission line, which is used to convey a signal from one point to the other. Now, so this is a transmission line equivalent circuit, in many cases, for simplicity of analysis, at first what we shall do is we shall assume that this R, which is the resistance, is very small, and this G, which is the conductance between the two lines, that is very high, so that we have the equivalent circuit consisting of only the inductance and the capacitance. This is L, this is C, and this is called a lossless transmission line. So we shall first take up the effect of this lossless transmission line on the performance of the integrated circuit, and then we shall consider the effects of, say for example, the resistance on the line subsequently. Now, what is this effect of this transmission line? Now, let us take a particular case. Suppose we have a voltage source, and then we have a switch, and then this is the transmission line which transmits the signal, and then of course we may have a load resistance. This voltage V. Okay. Now, suppose at t is equal to 0, the switch is closed. Okay. Now, when the switch is closed, what happens is this voltage waveform, it is not immediately available at the load end. The voltage front will move with a particular velocity. That is, if you take, say, if you call this point x is equal to 0, this point x equal to x1. Okay. So, at t is equal to t1, the voltage, if you plot the voltage across this line, okay, that t is equal to t1, this is what you see. That is, the voltage wave front, the voltage front has moved by distance x1 at, say, time t is equal to t1. Okay. At time t is equal to t2, it may move to the point x2. So, and this is V. So, this voltage V is not instantaneously available at the load end. It moves with a particular velocity V. Okay. And so, if it has moved x1 at time t1, then the velocity will be given by x1 by t1. So, this is the velocity of the wave, okay, the voltage front. Together with this voltage front, you also have a current front which also moves. That is, if you, the current along this line also will move, and there will be a particular ratio between the voltage and the current. Okay. So, if this voltage is V at this point, if you take the current will be I, which is related to the voltage V, okay, by a certain ratio. We shall come to that. So, this voltage moves with a velocity V. Now, what is this velocity of this voltage front and also the current front? It can be shown that the voltage, the velocity V is given by 1 by root of LC, where L is the inductance per unit length and C is the capacitance per unit length. So, that is the velocity with which this waveform will move along this line. Okay. Now, L is the inductance, C is the capacitance. And so, what is the delay of this line? Delay of the line is L by V. So, this will be L into root of LC. So, now since L is inductance per unit length and C is capacitance per unit length, we can write the delay as root of L prime and C prime, product of L prime and C prime, where these are the total inductance and total capacitance of the line. Okay. L prime is L into the length of the line, and C prime is the capacitance per unit length into the length of the line. So, this is going to be the delay of the line. So, for a particular line, there is an associated delay. The time required for the wave to move from the source end to the load end. Okay. Now, this velocity, which we have expressed as 1 by root LC, can also be expressed as 1 by root of mu by mu into epsilon, where mu is the permeability and epsilon is the permittivity of the space between the between the pair of lines here. So, that is the permeability and permittivity of the space. So, you see that one interesting aspect is that the velocity in fact depends on the medium, okay, the properties of the medium between the two lines, and not really dependent on the property of the line themselves. Okay. Now, this can also be expressed as C naught by mu r epsilon r, where C naught is the velocity of light in vacuum, and epsilon r is the relative permeability, and mu r is the relative permeability, and epsilon r is the relative permittivity of the intermediate space between the two lines. So, the C naught, as we know, is 3 into 10 to the power 10 centimeter per second. Now, if we assume the intermediate medium to be air, so if mu r and epsilon r are both equal to 1, so V C naught. Now, for say silicon dioxide, if the intermediate medium is silicon dioxide, which is, we know, the dielectric material which is used in silicon devices, okay, over which the interconnect lines will run. So, we have epsilon r is equal to 3.9. So, this gives us a velocity of 1.52 into 10 to the power 10 centimeter per second, 1.52 into 10 to the power 10 centimeter per second. Okay. So, which can also be written as this velocity. A better way to write it is this is equal to 15.2 centimeter per nanosecond. Okay. So, in 1 nanosecond, the wave will move by 15.2 centimeters. Okay. So, that is the velocity with which the wave front will move. Okay. So, as we see, we see that it is not instantaneous. The wave front, the voltage, okay, at the source end of the line is not instantaneously available at the load end. So, there is a time lag involved. Okay. All right. Now, coming back to the ratio of the voltage and current on the line. Okay. This voltage and current on the line will have a ratio which is given by R naught, which is called the characteristic impedance of the line. Okay. So, as the voltage front moves along the line, there is a corresponding current front which also moves along the line, and the ratio of the voltage and current is given by R naught. So, let us calculate the value of R naught. So, as the voltage front say here, okay, moves by a small amount of dx, say from the point, any point, it moves by a small amount of dx. So, the extra capacitance that has to be charged on the line is, say, C into dx. Okay. The extra capacitance, because C is the capacitance per unit length, and so if the wave front has moved by a distance dx, so the extra capacitance is C into dx. Okay. So, we say dc, say, is equal to C into dx. That is the extra capacitance. So, C is the capacitance per unit line. Okay. So, I shall put it C prime, the total extra total capacitance. Now, so what is the extra charge? What is that is required? That is this is the capacitance, the voltage, it was charged by a voltage V. Okay, so V C dx. All right, so that is the total charge, and therefore the current now. Okay, the current is given by, we know dq dt. So we get V C dx dt, which is nothing but the velocity. Okay, so we get V C V. Okay, now this V C V, V is given by we have already seen V is nothing but 1 by root LC. Okay, so 1 by root LC. So this gives us V root C by L. Okay. Now if you write I as equal to V by R naught, okay, we can see that R naught is equal to root of L by C. Okay. So this is the characteristic impedance of the line. It is related to the inductance per unit length of the line and the capacitance per unit length of the line. Okay. So in fact, if you bring the two lines, okay, it is basically in this transmission line, if the two lines are brought closer to one another, the capacitance goes up, okay, the inductance goes down, so R naught will go down. So it basically also depends, the characteristic impedance of the line will depend on the geometry of the line. Okay. So basically the transmission line which we have, as you have seen, is characterized by these two parameters, that is the delay of the line Td, okay, which is, as we have seen, is given by the product of Td, which is given by the product of root of the product of the total inductance and total capacitance of the line, root of L prime C prime. So this is the delay of the line, and the characteristic impedance, which is R naught equal to root L by C. So these parameters. Okay. So with the help of this analysis, we shall now see the effect of these of the transmission line, okay, on the performance of the integrated of this we shall see the effect of this transmission line on the effect of the signals which are to be transmitted from one point to the other. So we have seen the two parameters, the delay line and the characteristic impedance. Now let us look at the effect on a transmission line. So suppose we have another signal source and voltage V, and we have a transmission line. Okay. Now if this transmission line, as we have seen that a voltage front and the current front will move along the line, okay, and the ratio is given by the characteristic impedance R naught. If this transmission line is infinitely long, then this these voltage front and current fronts will move along this line, maintaining this ratio. There is no problem. Now again, if we assume that there is a load resistance, and the load resistance is equal to the characteristic impedance, again what will happen is the voltage front and the current front will move, maintaining a ratio of R naught, and once they reach the load end of the line, again since the load resistance is also R naught, there is no problem, because again the voltage front, the ratio of the voltage and current at the load end is equal to R naught. But suppose this load resistance is not equal to R naught, that is R not equal to R naught, then what happens? We have along the line, as the voltage and current fronts are moving, the ratio of voltage and current is R naught, but at the load end the ratio of the voltage and current has to be R, which is not equal to R naught. So how do we take this into account? That is having a ratio of R naught along the line, but having a ratio R at the load end. So, this can be explained or this can be sort of taken care of if we we consider reflections from the load end. That is, there is a transmitted wave and there is a reflected wave. That is, a part of the wave which moves to the load end gets reflected back from the load to the source end. Okay. Now, the reflected wave, okay, the amplitude. So, if the transmitted signal amplitude is V, okay, the voltage, transmitted voltage is V, the reflected wave, okay, is going to be rho into V, okay, where rho is called the reflection coefficient. Okay. So, the voltage, reflected voltage is rho V. Now, so the total voltage at the load end is going to be V plus rho V. Okay. And if the current I is the incident current at the load end is I, then the reflected current is going to be I is equal to rho I, but it is directed in it is in the opposite direction to the incident current. So, it is going to be minus rho I. Now, this I is equal to V by R naught, okay, because that is the ratio of the voltage to current in the line. So, V by R naught is the incident current. So, the reflected current is going to be minus rho V by R naught. Okay. So, we can write this V by R naught minus rho V by R naught. So, this is the ratio of the voltage and current at the load end, okay, and this should be equal to R. Okay. So, V by plus rho V divided by V by R naught minus rho V by R naught is equal to R. Okay. Now, from this, okay, we can just find out the value of rho. Rho can be expressed as R by R naught minus 1 divided by R by R naught plus 1. Okay. So, this is the expression of rho, okay, which is the reflection coefficient. So, it is related to the ratio of the load resistance to the characteristic impedance of the line, characteristic impedance or characteristic resistance of the line. Now, this from this we can see that rho will always lie between plus 1 and minus 1. The value of rho is always between plus 1 and minus 1. So, when R tends to infinity, that is it is a sort of open circuit, okay, rho will be equal to 1, and when R tends to 0, that is a short circuit, rho will tend to 0. Okay. So, that is if it is a short circuit, sorry, rho will tend to minus 1. So, sorry. So, this the extreme values of R, that is when it is open circuit, rho is going to be plus 1, and when R tends to 0, that is it is a short circuit, then the rho will tend to minus 1. So, these are the ranges of rho. Rho can lie between minus 1 and plus 1. So, all intermediate values of for all intermediate values of R, rho will lie somewhere between plus 1 and minus 1. Okay. So, with these values, with this so knowing the values of R and R naught, we can calculate rho, that is the reflection coefficient, and from that we can analyze, okay, the effect of the transmission line on the signal. So, that is what we shall take up next. Okay. Now, let us consider a voltage source V having source resistance Rs. Okay. This is driving a line, a transmission line having a characteristic resistance R naught and a delay Td, okay, and we have a line load resistance of RL. Now, let us see, let us take some values for these, all these quantities here on the board, and try to see how the what is going to be the nature of the waveform, how to calculate or how to analyze the nature of the waveform. Suppose V is equal to, it's a DC voltage, 12 volts, okay, and so we also have a switch here, okay, so it's turned on at a time t is equal to 0. Let Rs is equal to say 20 ohms, R naught say is equal to 100 ohms, RL is equal to say 900 ohms. Okay. So these are the different resistances, and the voltage source V is driving that line. Okay. Now, if we were to assume that this transmission line is basically a short circuit, then what do we expect? So as soon as the switch is closed, the output voltage, the voltage across the load resistance will be equal to V output or VL across the load resistance, VL is equal to RL by RS plus RL into V, that is equal to 900 by 20 plus 900 into 12, okay, that may be almost say about 11.7 volts. Okay. So the the voltage at the load end will be 11.7 volts. This is if we neglect the transmission line properties. But let us see what we are going to get if we now analyze it from a transmission line point of view. Okay. Now, in order to do that, what we have to do is we have to calculate the reflection coefficients at the load end and the source end. That is the first thing to do. So rho L is equal to, we have already seen the expression for the reflection coefficient. So that is going to be RL by R naught, that is 900 by 100 minus 1 divided by 900 by 100 plus 1. So this is going to be 0.8. Rho S, that is at the source end, will be 20 by 100 minus 1 divided by 20 by 100 plus 1. So that is going to be, this is in fact going to be negative. Okay. In fact, when the load resistance is less than the characteristic resistance, rho is always negative, and when the load resistance is greater than the characteristic resistance, it is rho is always positive. So this works out to minus 0.667. Okay. So that is these are the reflection coefficients. Now what we do is to find out the waveform, there is a particular diagram which is drawn. Okay. It is drawn like this. So suppose this is the so this axis on this side is the time. So suppose the waveform, this is 0, say this end it is 0. Now this is the source end, this is the source, and this is the load. Okay. So it takes a time Td for the waveform to move from the source end to the load end. Okay. Now what happens is initially a voltage front will move from the source end to the load end. Now what is the value of the voltage front? So here you see that this is at this end, this is R naught and this is Rs. So at this point, if we say a voltage V prime is there which is going to move, what is the value of this voltage V prime? V prime will be equal to R naught by R naught plus Rs into V. So that is equal to, in this case, R naught is 100 and Rs is 20, so into V, that is 12, so that will give us 10 volts. So a voltage front of 10 volts is available here at the source end of the transmission line, which is going to move towards the load end of the line. Okay. So if you come back here in this diagram, so this is the at time t is equal to 0. At time t is equal to Td, you have a 10 volt. Okay, this 10 volt front moves and reaches the load end. Okay, all right. Now this gets reflected. Okay, and the reflection coefficient is at the load end rho L. I'll write it here is 0.8. Okay, and at the source end rho S is equal to minus 0.667. So the reflected wave here, it is 0.8 times the incident wave. So this one is 8 volts. Okay, so this 8 volts, 0.8 times 10, 8 volts gets reflected and reaches the source end at twice Td. Okay, so if you now observe the waveform at the load end, okay, at Td, which is equal to the delay of the line, okay, the voltage which is the voltage you have is 10 plus 8 is equal to 18 volts. So if this is say 10 volts, 20 volts, 20, 5, 15 say. So it goes all the way, the waveform, it goes all the way up to 18 volts at t is equal to Td. Okay. Now again here, again we come back to this diagram. So this 0.8 volts has gone back to the source end. Now again this is going to get reflected from the source end with a reflection coefficient equal to minus 0.667. Okay. So the value of this is equal to so 8 into minus 0.667 will give us minus 5.36. Okay. So all right, and then again once it reaches, this is going to reach here at 3 Td. Okay, and then again you have another reflection at 3 Td. This is again the value here is going to be 0.8 times minus 5.36, which is equal to 4.29 minus 4.29. Okay, so what happens is at t is equal to 3 Td. If you go back to this diagram, okay, now the voltage is equal to the sum of all these components, 10 volts plus 8 volts minus 5.36 minus 4.29. So this waveform, this voltage here is due to the wave, the voltage which started off 3 Td back and underwent this reflection, the wave which started off Td back and underwent this reflection. So we have to add up all these components. So if we add up all these components, we find that this is going to go down to 8.35. So this is actually 18, this is 8.35. Okay. So again, so this is 4 Td. Again, this goes back here at 5 Td. Okay, and so this value here is 2.86. Then again, 0.8 times that is going to be 2.29. So at 5 Td, the voltage will go up to, this is the sum of all these components. So this goes up to 13.5. Similarly, if we carry on this analysis, we find that at 7 Td, so this is 5 Td, at 7 Td, it goes down to 10.77. So finally, what we see is, if we carry on this analysis for more lengths of time, you will find that it finally settles down to the value of 11.7 volts, which is the expected value. Okay, so it will go up like this and then down, and finally it will settle down to this value of 11.7 volts, which is the one we expect, the voltage we expect if the transmission line is to be neglected. So in actual practice, we will have a waveform which we see is very much distorted. All right. So and it takes some time to settle down to the final value. So this is the effect of the transmission line on the signal. Okay. Now we have taken a particular case of a particular problem, okay, where we have defined the source resistance and the load resistances. Now, if we were to take say, and let us take an extreme case, say for say RL equals infinity and RS equals 0. Okay? Then what happens? In that case, what we get is rho L will be equal to 1 and rho S will be equal to minus 1. Okay? Plus this rho L is plus 1 and rho S is equal to minus 1. And then if we have an incident waveform V, okay, what we will observe is at the load end, we will observe that the output waveform is going to be something like this. That is, this is V, okay, this is 2V. Okay. So basically, you have oscillations of this amplitude 2V, okay, and this is never going to die down. Okay, this is going to continue indefinitely. Okay. So we find that this in the extreme case of one side being open circuit and the other side being short circuit, okay, you have a situation where there are oscillations and this is never going to die down. The important thing is at the source signal is actually something like this, okay, and due to that you are having something like this. Now, in the actual circuit, if this is going to drive a clock of a flip-flop, what you expect is that for example, the clock of a shift register, say, you expect the register, there is going to be one single shift, okay, but what you get is a number of waveforms, and the shift register will see a number of clock pulses at the input, so that there is going to be multiple shifts. So all your what you have designed, the circuit is going to go haywire, and you are going to get something which is totally unexpected, and you would not know what is happening. But of course, this is the extreme case. Okay, that is rho L 1 and rho S is equal to minus 1. In other cases, as we know that rho is less than 1, okay, the magnitude of rho is less than 1, which means that the with reflections, okay, the reflected wave is going to ultimately die down because rho is less than 1. The amplitude of the reflected waves ultimately die down. But of course, it's over a period of time, so you get a lot of delays, as well as, of course, a lot of distortion, as you see here. So we have seen that if you have a line which is short circuited at the source end and open circuited at the load end, and if you have a waveform like this, voltage V, okay, at the source end, that is, when we close this switch here, okay, we get a waveform as step input at the source end of the line, the output is going to be something like this, oscillations, okay, and which are not going to die down, okay, of amplitude twice V. So this is of course going to be a very bad situation, okay, and this is, of course, this is the extreme case, okay, that is one end short circuit and the other end open circuit. Now let us take another case, similar case, where again the load is open circuit and the source is short circuit, but the input waveform, okay, that is the input waveform V, is not a step input, but it is actually a ramp input like this. Okay, that is, it takes time 10 TD, okay, to rise to 10 volts. That is, the waveform rises to 10 volts at time 10 TD. Okay, that means for every TD it rises by 1 volt. Okay. Now, if we have such a waveform, and if we still have the same conditions, that at the load end it is open circuit and at the source end it is short circuit, what is the output waveform? Let us look at it. Okay. In that case, okay, again if we take the same diagram, okay, what we have is at time TD, at t is equal to TD, okay, what we have is the output voltage is equal to, of course, let us draw this diagram. Okay, then if this is 0, if you have a voltage V here, okay, this is plus 1, rho L is plus 1, so this you will have V, okay. This one, there is rho S is minus 1, so this one will be minus V, this one will be again minus V, this one will be plus V, this one will be plus V. So this is TD, 3 TD, 5 TD. Okay. So now, so at T is equal to TD, you have twice the voltage, okay, which started off at time TD before. So you have twice V T minus TD. Okay, that is the voltage at time T minus TD. So at voltage at time T minus TD is at voltage at time T is equal to 0. For this ramp, this is equal to 0. So the voltage is equal to 0. All right. Now at T is equal to 3 TD, voltage output will be equal to at this point, okay, it is going to be twice the voltage which started off at time TD before from the source end, and minus twice the voltage which started off at time 3D before, that is from the source end. So we can write V output is equal to twice voltage T minus 3 TD plus twice the voltage, minus twice the voltage, twice the voltage T minus TD minus twice the voltage T minus 3 TD. Okay. Now V T minus TD, now it is 3 TD. So what was the voltage at T equal to twice TD? From the ramp we can see that at T is equal to twice TD, the voltage is 2 volts. So we can write is equal to 2 into 2 minus T minus 3 TD is T is equal to 3 TD is 0. So this is 0. So you have 4 volts. So the output voltage, I'll draw it here, okay, at T is equal to TD it is 0. This is TD, it is 0. At T is equal to 3 TD, it goes up to 4 volts. Okay. So let us suppose this is the ramp which we are talking of. Okay. Now that is the input ramp. Okay. So the output, this is 4 volts at T is equal to 3 TD. Okay. Now at T is equal to 5 TD, okay, what happens is you have again V output will be equal to again if you look at this point, it is going to be twice the voltage which started off TD before minus twice the voltage which started off 3 TD before, and twice the voltage which started off 5 TD before. So twice V T minus 5 TD plus twice minus twice V T minus 3 TD plus twice V T minus TD. So this is going to be equal to this is 5 TD, at T is equal to 5 TD. So this is twice V 0, which is 0, minus 5 minus 3 TD is 2 TD. So at 2 TD it is 2 volts. So minus 2 into 2 plus this is 4 TD. 4 TD is 4 volts. So this is 2 into 4. So this 8 minus 4 is equal to 4 volts. So at 5 TD, it still remains at 4 volts. So if you continue this analysis, we will find that what you get is the output is going to go like this. So this becomes like this. It is going to go like this. So we have the input ramp here, straight line, and this is the output, which goes like this. Okay. So what we see is that the output almost very closely follows the input in this case. Although this is the situation, okay, where the output is open circuit and the input side is short circuit. This is the same situation if you have a unit step. We have seen how serious we have the problems we have. So the conclusion is that if the input waveform is slowly varying, okay, then the transmission line effects are going to be minimal. Okay, the distortions due to the transmission line is going to be very small. So only when the rise time of the input waveform is very small compared to the delay of the transmission line, okay, the transmission line effects become more dominant. Okay. So this again I just repeat that only when the rise time of the input waveform becomes small compared to the delay of the line, then only the transmission line effects become dominant. So in fact, it is a rule of thumb to say that the transmission line effects become dominant when the delay time of the line, okay, the delay time of the line, that is TD, okay, that is the delay time of the line is going to be more than, okay, the rise time by 5. Okay. So, or in other words, we can also say when the rise time, okay, is less than 5 times the delay time of the line, okay, then one has to actually look into the transmission line effects. Okay. This is a rule of thumb which is used to demarcate the when the transmission line effects are dominant or when we can neglect the transmission line effects. Now, if we look at the different rise times, for example, if from this, if you have a rise time of say in picoseconds, say if you have 1000 picoseconds, that is 1 nanosecond of rise time, okay, then what is the critical length of a line, okay, when you have to start thinking of the transmission line effects? Okay, that is what we have to consider. Now, suppose if we assume a velocity as we have done of the wave in the line as 15.2 centimeter per nanosecond. Okay, if this is the velocity of the waveform in the line, that is we have already seen this value for silicon dioxide dielectric. Okay. Now, for this, the critical length of the line, okay, L critical, okay, is given by, it is going to be in millimeters, 30 millimeters. That is, if the rise time is 1000 picoseconds, then if the critical length of the line is less than 30 millimeter, if the line length, which the interconnection length is less than 30 millimeter, then we must watch out. We have to consider the transmission line effects. Now, if it goes down to 100 picoseconds, then this will also go down to 3 millimeters. That is, if the rise time is 3 picoseconds, okay, if the rise time is 100 picoseconds, then the critical length of the line is 3 millimeter. Okay, that means for this, if the line length goes down to below 3 millimeter, we have to be careful. Similarly, it scales linearly. So if you go down to 50, this one will be 1.5. Now, these values, 100 picoseconds and all, well, and these are not so uncommon values nowadays. Okay, we have the rise time and fall times of this order. So this 3 millimeter, especially, say for example, 3 millimeter, if you are have something on a PCB, of course, we have to be very careful. We must consider the transmission line effects. Even if we go to very high speed circuits, we may even have to consider transmission line effects on the chip. Okay, so these are some of the delays. Now, what we have to look for now is that there are different models which can be used to analyze the circuit when we go to such small dimensions of lines, okay, or such small rise time and fall times. Now, which is the correct model to take to simulate the line, okay, simulate the effects of the transmission line. So that is what we shall take up next. Now we shall look at the different models which are used to represent the transmission lines, and the particular models which must be for the particular situation, okay, which is the best model to use, okay, in order to simulate the transmission line. Now suppose we consider the transmission line, we replace the transmission line by just equivalent capacitance, say C. Okay, and of course you have the source resistance, okay, from the voltage source. Okay, now this if you have just this model which is called the C model, okay, then, and if you consider open circuited line at the load end, okay, then we know that the output voltage is going to be V naught, output voltage is equal to V 1 minus e to the power minus t by Rs, that is the source resistance, into C. Okay, the C prime, which is actually the total capacitance of the line. So we actually replace the line by its total capacitance, that is the C model. The output voltage would be given something like this, that is the output voltage when you have a step input, okay, the output voltage will rise like this and finally reach this value. Okay, and in this situation the rise time is given by 2.2 Rs C prime. Okay, now so this is the situation if we have only a lumped capacitance to replace the transmission line. Now we can show that this in this situation, okay, we can so in this case the rise time is given by Rs into C prime, okay, whereas the delay of the line, okay, the delay of the line is given by L by V. Okay. Now if we have a situation where the rise time, we have already said that the transmission line effects becomes minimal when the rise time is very much greater than the delay line. So TR very much greater than TD would imply that Rs C prime is very much greater than L by V. Okay, L by V is nothing, V is, we have already seen, is equal to L by V is equal to TD, and which we have already seen is equal to related to the inductance and capacitance of the line, and or in other words Rs C prime is very much greater than root L prime C prime. Okay, and now the L prime and C prime is equal to L prime is L into the length of the line into L, and C prime is the length of the line into C. So we can write this as, or Rs is very much greater than root of L by C, and root of L by C we know is equal to R naught. So Rs is very much greater than R naught. So we can say that when Rs is very much greater than R naught, okay, when that is the source resistance is very much greater than the characteristic impedance of the line, the rise time of the waveform is going to be very much greater than the delay line, and then what happens is we need not consider the transmission line effects. The transmission line effects become minimal, and in fact the line can be replaced by the capacitance of the line. Okay, just the capacitance of the line. This is because if we go back to our earlier model, okay, the analysis how we have analyzed, okay, what we have seen is that if we have a transmission line, this can also be, we get the same results from using transmission line. That is, if you have a transmission line, the input voltage to the transmission line is given by V prime, which is equal to R naught divided by Rs by R naught into V. Now if R naught is very much less than Rs, Okay, that is the source resistance very much greater than the characteristic resistance. V prime is going to be very much less than V. Okay, so the input voltage at the source end of the transmission line is very much less than V. So if the output voltage has to rise to V, it can only be through small increments. Okay, when the multiple reflections take place. So if you do a transmission line analysis here, okay, so you have V prime coming here, and then it will go up. So you're going to have a situation like this. Okay. So transmission analysis will give you something like this, whereas if you just replace the line by lumped capacitance, you get something like this. So a lumped capacitance, okay, so the C model which we have here, that is replacing the line by the capacitance, is valid when you have Rs very much greater than R naught. Okay, that is the source resistance is very much greater than R naught. Okay. Now in this case, of course, we can neglect the actual resistance of the line, because the source resistance is so high, it plays a dominant role. But when we go to Rs, so this is valid when Rs is very much greater than R naught. Okay. Now when Rs lies between 10 times R naught and R naught, okay, then we cannot really neglect the resistance of the line also. Okay. Then we have a model. Okay, and what we can do is we can use the resistance of the line. The line can be replaced by its resistance and capacitance, RC. Okay. This is called the L model because of the shape of the model. This is the resistance of the line, this is the total capacitance of the line. But this type of model does not give very correct results, because we know that the resistance and capacitances are distributed, but this is using as a lumped values. So what is done is 3-section pi model is generally used, okay, which is given like this. So you have C by 6, R by 3, okay. So the line can be replaced by what is called a 3-section pi model, where you have these capacitances here, okay, and these are the resistances of the line. So basically we do not have a single resistance and capacitance, but this is distributed, and we find that this gives the more accurate delay values for the line. In fact, if we take the lumped value, that is only one resistance and one capacitance, okay, it is going to be something like this. This is for lumped. Okay, if you take a distributed value, it goes like this. So this is voltage versus time. Okay, so this is distributed. So this gives a more accurate representation, okay, and the lumped representation gives a higher delays, okay, than what is to be expected normally. So this is called the 3-section pi model or the P3 model, okay, and this can be used when for this situation. For when the source resistance becomes less than the characteristic resistance, we have to go for transmission line analysis. In fact, we must remember that the transmission line analysis is always correct. Okay, it always gives the best results, but only that in many cases it may not be necessary to go into the transmission line analysis. We can use these simple models to get results which are which is similar to the transmission line results and with much less computation time. Okay, so that is the advantage. So just briefly to conclude, I'll give some values, okay, showing I'll give a table showing the different models okay, and when to use the particular model. Okay. For example, if we take a look at this table, okay, now suppose this shows the values of Rs by R naught. Okay, this is the values of Rs by R naught. Suppose Rs by R naught is equal to 10. Okay, then we have to take the capacitance model. Okay, and here, okay, so this is 10. Let us take some values 2, okay, 1, and then 0.2. Okay, so these are for different values of Rs by R naught. Here I am showing different values of R by R naught. Okay, that is the resistance, actual resistance of the line when compared to R naught, 0.2, 0.5, 1, and 2. Okay. Now, here of course, this means that R is very much less than R naught. So, in fact, when we go for this situation here, that is Rs by R naught is equal to 2, we should actually take the C model, but we should actually take the P3 model. But since R is very small here, okay, we can take the C model. That is, we in fact neglect the resistance of the line. So, in all these situations, when Rs is very much greater than R naught, we can take only the capacitance of the line. Okay. But when Rs becomes comparable to R naught, we must take the P3 model, that is a 3-section pi model. When Rs and R naught becomes comparable, and when Rs becomes less than R naught, okay, one has to go for transmission line analysis. So, we, for transmission line also we have two models. One is the normal one-section transmission line, okay, which we have already seen. Okay, but when the resistance of the line becomes comparable, that is, it is a lossy transmission line, we have to go for what is called a 4-section transmission line model. Okay, that is basically you have a structure like this. One more section here. Okay, so this is a 4-section transmission line model. Okay, so these are all transmission line. This is characteristic impedance R naught and delay TD by 4. Okay, R naught TD by 4, R naught TD by 4, R naught TD by 4. This is R by 3, R by 3, R by 3. So, together these three make up is equal to R, the total resistance of the line. Okay. So, you have a 4-section transmission line model. This is called the TRL transmission line 4 model. Okay. Now, if you have one transmission line section, that will be the TRL1 model. So, when the resistance of the line is small, okay, you can take the 1-section transmission line model. But if the resistance of the line becomes large, okay, we have to go for the 4-section transmission line model, which includes the effect of the resistance of the line. That is, it basically considers lossy transmission line. So, this table gives the different models which can be used for different situations. Again, I would like to reiterate that the transmission line model is always the most accurate, but it takes more amount of time to do an analysis. So, when we have a particular situation when it is possible to get the same results using just a lumped capacitance, it would be a waste of time to go for transmission line models. So, this capacitance model would suffice. So, we would always when we do an analysis, we have to look at the particular situation and see which model will give us the best the results best results in the shortest amount of time, simulation time. So, this table we can do the simulation in the shortest possible time. Okay, for example, we can just take a capacitance model in some situation and get the same results as the transmission line model, and in a much shorter, smaller amount of time. So that is, we should always go for that. So with that, we come to the effect of the of this discussion on this effect of interconnections, and we have seen that interconnections give rise to a lot of delays and as well as distortions. So we must be aware of that. We must use the correct model to simulate the circuit, that is, include the interconnection model, which are available in circuit simulators such as SPICE, and then do the simulate the circuit to get the best results. Otherwise, when we fabricate a circuit, we may get results which are totally unexpected, and we would run into problems. So interconnections play an important role also in digital circuits, and that must be emphasized, especially when the rise times become small, that is, in modern day high speed digital circuits.